Hello students, let's begin lesson 7, optimization. What is optimization? Either maximizing or minimizing. That's basically what we are up to here. Okay, in reality, sometimes we have to take more than one maximization or minimization put together, maximizing something while minimizing the other kind of situation. But this is 1000 levels, so we do not consider multivariable calculus. Either maximizing my profit or something great, or minimizing my loss or something bad. That's basically what we are up to. Therefore, we are looking for things like these. Among the critical points, either this kind of situation, minimum, or that kind of situation, maximum. Let's consider the simplest type of example associated to those. That's the absolute extrema problem. A continuous function defined in a closed interval always have the absolute maximum and the absolute minimum, the biggest value and the smallest value. The question is, however, when do we get that? Well, here's an example problem. F of x is x cubed plus x squared minus x in the interval -1 to 1. Okay, how do we start? Always begin with plotting. Plot it, and what do you anticipate? Looks like you have absolute maximum pretty close to 1, either at -1 or at +1. It's a little bit difficult to say which is higher, but clearly we have to look at either this endpoint or that endpoint for the absolute maximum. For the absolute minimum, somewhere down here, a little bit less than 0.5, a little less than 0.4, somewhere here. That's the absolute minimum. Now, these are coming from the endpoints, so we can just plug in x equals to -1 and x equals to +1 here and do my computation, and I'm going to guess the maximum value. The biggest one will be the maximum value. No problem there. Now, this one is going to be a bit bigger challenge because I have to find out what number to plug in first. We need horizontal tangent here, basically this. So somewhere here, we need a point with horizontal tangent. So the slope or the derivative at this point should be equal to 0. So that'll give me my appropriate x value. And then once you find out that x value, then I can plug into this function and then find out the minimum value. Finding out the x value is a big deal. Finding out the minimum value is relatively less of a deal because once you have that x value, plugging in and getting that function value is just a calculated work. This is the big deal. Make sense? By the way, for these, you're looking for the endpoint value. Just straight up plugging in and running your calculator. No big deal, but you have to do it anyway. And then for this one down here, you have to solve this equation. Take the derivative and set it equal to 0. That is the big deal. So is everybody okay with the strategy? 2 things to do. Checking the endpoint, easy. Checking the horizontal tangent, big deal. All right, let's go. Okay, let's open it up. I did the big deal first. Okay, all right. Here's the graph. I'm looking for somewhere here. Horizontal tangent. I'm going to take the derivative and set it equal to 0. And that's what I did. Take the derivative and set it equal to 0. What do we have here? We have a quadratic equation. Oh, quadratic equation, no big deal. Just factor it and find out. That's basically what I did. And I got x equal to -1 and x equal to 1/3. Look at the graph. X equal to -1 versus x equals 1/3. Which one is the one that I want? Clearly, it's the 1/3. That's that's the absolute minimum. Do you see that? It's x equals to 1/3. And if I do that, I'm going to get negative 5/27, about 0.185. And let's look at the graph. This is about 0.2, negative 0.2, so negative 0.185. Yeah, that makes perfect sense. So we have that absolute minimum, and that coming from taking the derivative and set it equal to 0. It's not too bad. Take the derivative, set it equal to 0. It's just a quadratic equation to solve. And then, as for the endpoints, no big deal. Just plug in x equals negative 1. Just plug in x equals to 1. Turned out they're the same. So we have tied. So that's the absolute maximum. And here, absolute minimum. Here's a conclusion. F attains the minimum, or absolute minimum, negative 527, excuse me. Bigger font. Yeah, negative 527, not 517. I misread it earlier. Negative 527 at x equals 1/3. That's the absolute minimum. And absolute maximum 1. And that's shared at x equals negative 1 and x equals positive 1. Always begin from the graph. Let's see. Do we have time for another problem? Okay, here we go. A little bit more complicated function, so it looks like a little bit more challenging computation will follow. Let's see. Plot it. Plug 8x squared minus x to the 4th power and plot it from x going from 1 to e. That's a plot. Okay, all right. Clearly, we are looking for this endpoint, not the other one. So right-hand side endpoint, x equals to e, will give me absolute minimum. Is that clear? All right. Absolute maximum will be somewhere around here. Looks like around x equals to 2. Do you see that? So around here, I have horizontal tangent. X equals to about 2, I suppose. So in any case, I have to take the derivative and set it equal to 0. That's what I have to do to find out the absolute maximum. Now to find out the absolute minimum, it's right here. So f of e, that's the absolute minimum. And this is no big deal. It's just a calculated work. And this one, that's a big deal. Take the derivative and set it equal to 0. That's an equation. That's a derivative computation using the chain rule. That's a big deal. Okay, stop the playback and try it on your own. Have you? Let's see. What did I do? Okay, take the derivative and set it equal to 0. Is that the derivative? Well, it's a log function. So derivative of log function is 1 over x. Log of x becomes 1 over x. But instead of x, we have something complicated here. So apply the chain rule. Inside never changes. That's what I get. And by chain rule, multiply the derivative of the inside, which is 16x minus 4x cubed. So multiply this derivative to the numerator, and that's how you get this expression there. That's how. And then setting this one equal to 0 means setting the numerator equal to 0, so you can set it equal to 0 and solve it. Here, I'm forgetting x. Yeah, this is cubic equation, so. Anyway, yeah, all right. There's x and x down there, so maybe I should have done this like this. But come on, who cares? Set the numerator equal to 0 and you'll see x equal to 2 is the only solution within this interval. X equal to negative 2, that's outside the domain. X equal to 0, that 2 is outside the domain. X equals 2, that's it. Just take the numerator and set it equal to 0. It's not a difficult equation to solve. You get x equals to 2, and you can verify with calculator. if you plug in x equal to 2 and run this computation, you're going to get log of 16, which is about 1.94 something. Okay, all right. Apparently that's what I got. And here's a graph again. Okay, this value here, and then that value over there. And by the way, if I plot everything, you get this dotted curve. Interesting, isn't it? Okay, we have another problem here. That's going to be a little bit more challenging, I guess. All right, how do you do this? So plot it first, and then this is what I get. So absolute minimum takes place at left-hand side endpoint, x equal to 0. And then right-hand side endpoint, no big deal. This one right here, I can expect a horizontal tangent at something greater than 0.5, somewhere here. So take the derivative, set it equal to 0, that's a big deal right here. And plugging x equal to 0, hey, that's no big deal. Big deal here, and no big deal there, and that's nothing. Do you see it? Okay, what did I do here? Big deal first or no big deal first? Okay, take the derivative and set it equal to 0. Alright, big deal first. Take the derivative by chain rule. And then I want to set it equal to 0, so I have to factor it. And common factor is e to the negative x, so I factored it out. So e to the x times this is equal to 0. And exponential is never equal to 0, so this thing is equal to 0. So we get this. This is an exponential equation. Okay, you can solve it. Solve it with respect to exponential, and then take the log of both. Eventually, you're going to get log of 2. Oh my, this is getting out of control. This is a good problem for Calculus 1, but I don't know whether this is good for 1325. All right, we started, so let's finish it anyway. X equals to log of 2 is the critical point. And then if you plug in x equals to log of 2 to this thing over here and run your calculation, you're going to get 1/4. Yeah, all right. That is the absolute maximum. Absolute minimum, as you checked before, is x equal to 0. You don't really have to consider this. You saw the graph already, right? This one, yeah. When x equals to log of 2, that's when we have absolute maximum. And right here, x equal to 0, that's when we have absolute minimum. This was easy. Plug in x equal to 0 and run your calculator. That's easy. Oh, this one was big challenge. Oh, wow. Taking the derivative and setting it equal to 0. Taking the derivative wasn't too bad, but setting it equal to 0, we ended with the exponential equation. And then solving those exponential equations, we ended up with logarithm. It's not impossible to do it here after all, because there's no trigonometry involved, but in terms of depth, wow, that was a big challenge. I don't know if that was appropriate. I don't know whether this was appropriate for this course. For Calculus 1, this was okay. That was great. But for applied calculus here, Maths 1325, probably not. Anyway, that completes section 1, and that is the easiest type of optimization. You have a function, and then you have an interval. In that case, number 1, plot it. Number 2, plug in the endpoints, as you see from the picture. And then number 3, the big deal. Take the derivative, set it equal to 0, and hope for the best. If you have some polynomial equation, yeah, you can do it. If you have something transcendental, probably either I'm in really nasty mood or it's an extra credit problem.